Okay, so right here, which give us an idea what to maximize. That is, we are going to maximize the margin, 2 over the L2 norm of W. And then this helps us to set up the following condition. This is the optimization problem we are going to set up, which is going to maximize the margin. That is right here, 2Z2. Okay, and now we are going to set up the cost like this. JW, the parameters we are going to choose, that is W. This W actually involve W0. So that means we are going to change, we are going to adjust the parameters W, that is involve W as well as W0. They are all unknown variable we are going to choose. So anyway, now we are going to minimize this J, and then now why, before I'm talking about the maximization of the margin, but now why I change it to minimization, and now we are going to minimize the L2 norm of W. So in that case, you can take a look at this one. If when the margin is maximized, when W is minimized, because 2 over W, that is mathematically it is more difficult to deal with. So instead of maximize the margin, we are going to do minimize W. Actually, they serve the same purpose. So that's why we are going to minimize the W, and then we put square right here, and then so as well as 1/2, because we are going to, when we have square right here later on, because we need to do the differentiation of the square term will cancel out this 1/2, to make it mathematical elegant. Okay, so this is the main purpose, minimize W, so that we are going to maximize the margin, and then subject to this condition. Now this condition, yi times this fx greater than equal to 1. So this one, that is, we are going to use this condition to cover two cases, +1 and -1. According to what we have done before right here, that means +1 case, +1 samples, which will give us always greater than 1 value. -1 will give us always negative value. So if we are going to multiply yi to, now right here, wtx plus w0, for +1, this one is always +1, greater than 1. The same for this one, that is wtx plus w0. If we are going to substitute causes into this equation, always it will give us negative value. And now, because the label right here, y that is +1, y here that is -1, I omit the I right here. I, it means that we are going to specify, say, which samples we are going to talk about. For example, this is x1, so xi, that would be this samples. So without I right here, it means that it could be any samples right here. Okay, and now we are going to multiply y for +1 case. For +1 case, because this is plus, this is plus. Okay, so this term will be always greater than 1 or equal to 1. Now this one, the same situation. If we are going to pass y to this wx plus w0, this term is always less than or equal to -1. This one is -1. Minus, it becomes always greater than +1. So multiplying yi right here, that is just to combine these two conditions, two cases together, and then it always greater than or equal to 1. If this value is always greater than or equal to 1, it means that we are able to 100% correctly classify these two set of samples right here. Yeah. Okay. So now I just explained the purpose of this term, that is to equivalent to maximize the margin. The constraint right here, that is to make sure that this Wxi plus W0 can make sure that all samples are correctly classified. Yeah. Okay. So this is the main problem, the pipe mode problem. That is, we are going to use the method of the Lagrange multiplier to handle the minimization problem with constraint. Yeah. So we are going to introduce the Lagrange multiplier. Lambda is a vector. So we have lambda 1, lambda 2, up to lambda n. Remember that n, that is the number of samples. That means corresponding to each sample, we have yi as well as we have a Lagrange multiplier, lambda I. So that means corresponding to each sample, we have the Lagrange multiplier right here. The dimension, that is n, depending on the number of samples we have in the data set. Yeah. So this is the pipe mode problem we set up for this constraint optimization problem. According to the existing result, this pipe problem can be transformed into this dual problem, which can be easily to be handled. So it becomes a min-max problem. Minimize the L subject to W and W naught. At the same time, we want to maximize this cost with respect to the Lagrange multiplier. Lambda I must be greater than or equal to 0. Yeah. So this is once we find lambda, and then later on you will just find out that once we find lambda, and then we can find W as well as W naught. Okay. So to start with the dual problem, we are going to minimize this cost with respect to W and W naught. So we are going to do the partial derivative of this cost with respect to W. Note that this is a vector. Yeah. So we have W1, W2 up to WD. Yeah. So this is the lowercase d, that is the dimension of W. So dLdW, which give us this W. So we find out that W, that is actually contributed by every samples in the data set. That is the sum of lambda I, yi times xi. The same partial L, partial W. We just find out that we need to satisfy this condition. Yeah, if we are going to maximize the cost with respect to W naught, the multiplication of lambda I times yi, the label, and then all together, that is 0. Yeah, so we have to satisfy 1 and 2. Now this is an example. Assume that we have a data set of 6 samples. This is x1, this is x2, this is x3. These 3 samples with the label -1. And then associated with them, we have lambda 1, lambda 2, and lambda 3. They are the multiplier, Lagrange multipliers. Now we have x4. This is x4. Okay, this is x4. And then with the label +1 associated with the Lagrange multiplier, lambda 4. And then this one, we call it x5 with the label +1 and lambda 5. This one, that is x6 with the label +1 with the Lagrange multiplier, lambda 6. According to 1, because n now that is 6, because we have 6 samples right here in this data set. So expand this summation term, we have lambda 1, y1, x1 corresponding to these samples, and then lambda 2, y2, x2 according to this equation. That is for x2 and so on. So in total we have 6. That means once we know lambda, we can find out W, because y1, x1, they are known right here. X is the data set. We collect that. Y1 up to Y6, they are the labels we give to the data set. We assign each point a label. From 2, we can just simply expand that. Lambda 1 times y1, lambda 2 times y2, sum of them, that is 0. Yeah, so that means it gives us some idea how to find the value of lambda. Yeah, so because now if we are able to construct some equations, and then we can solve the value of lambda. Yeah, okay, and now we are going to put 1 and 2 into L. That is, we put these two equations into this prime problem, or this one actually. Yeah. Now this one can be, the L can be reduced into this form. Yeah. Okay, so that means now the only unknown, that is lambda. So I'm not going to go through this mathematics, and then so I will leave it to you. It is some algebras. I think that everyone can do it. Now the dual problem is reduced into this one. Maximize this bit with respect to lambda. That is going back to this point, because we have done the minimization with respect to W and W naught, and substitute W and condition 1, 2 into this formula, so that the problem now is reduced to maximize this term with respect to lambda, subject to this condition. This condition, that is, we develop right here, and then because lambda I, that is greater than 0. So we are going to have this condition as well. Yeah. So capital letter N, that is the number of samples we have. Now we are going to look into the details about what we are going to do with respect to 3. Now we come up with a number of observations according to this slide. Okay, now according to this slide, lambda I, that is greater than 0, and then we need to find the lambda, maximize this function, and then the observation is that solution lambda I to 3, actually we can use a quadratic programming solver to solve it, because right here, that is the quadratic program we form. Yeah, so any standard quadratic programming solver, we can use it to find the solution of lambda. Yeah, if we turn it into a computer program. Now we also find out that this function, the whole thing right here, if you are going to substitute the value into this cost, it is a scalar function. That means which will give you a scalar value. For example, 1.2 or 2 point something. It is not a vector. And then the dimension of the input space, x, no matter what dimension it is, 1, 2, 10, it will not change the function. Yeah, it will not change the function from a scalar to a vector. Yeah. Also, lambda I, that may not be unique. That means when you use different way to solve the solution, lambda value may change. But according to 1 and 2, no matter what set of solution of lambda it is, which will give you the same W. Yeah. So different lambda, if the lambda they are the solution, W will be unique. Okay. We will also find out that for those xi, for those samples, they are support vectors, and then lambda I will not be 0. In that case, that means W will only be contributed by those support vectors. So W in equation 1 can be reduced to only consider those lambda, that is non-zero. Yeah. Okay. Now I will explain this why later on. So that means W can be contributed by those X belongs to subparameter NS, that is the number of subparameters, and then for those subparameters, according to what we have defined, that is, if X is support vectors, when you substitute those X into this fx, which will give you either +1 or -1 depending on the label of X. Yeah. Okay. Now take a look at this one. I'm going to explain why we obtained the result like that. Because we are going to maximize L with respect to lambda. So if we are going to look at this bit, W does not depend on lambda. That means when we are going to adjust lambda, we can only affect this term. Yeah. Okay. And now when you look at this term, this term is always greater than 1 or equal to 1 according to what I explained before. Yeah. If the samples, they can be correctly 100% correctly classified, and then this term will be greater than or equal to 1. So this term, if it is 1, now if we have two cases, the first term, that is, it is 1. So 1 minus 1, this term will be 0. Another case, that is greater than 1. Yeah, this term is greater than 1. So -1, which will give you a case that is greater than 0. Okay, so that means this term right here, that is either 0 or greater than 0, which will not be less than 0 if the samples, they can be correctly classified. So now this term, the whole term, that is greater than 0, that is positive, and this one, that is greater than or equal to 0. So in order to maximize this one, so lambda I times this term, which will give you a positive term. Okay, when we have a minus sign right here, and then so this minus positive term, that is always negative with the maximum value, that is 0. Yeah, so that means what we are going to do, if we would like to maximize L with respect to lambda, so this term we are going to make it to be 0, so that the whole term L right here can be maximized. Now, so we come up with this conclusion. If this term, that is this one, that is greater than 0, we are going to set lambda I to be 0, so that the whole term right here becomes 0. When this term equals 0, and then we allow lambda I to be non-zero, but the multiplication, lambda I multiply this term right here will become 0. That means no matter what, the second term right here, it is 0. Either the yi times this thing equals 0, or lambda I, that is 0. Okay, if you are going to look at this condition, under what situation this term will be 0, that is only when xi, that is the support vector. It is because when we refer to this diagram, if we are going to substitute the support vector into this fx, it will give us +1. When this guy substitute it into fx, it will become -1. So only the support vectors, they will give us this condition. This one will become 0. So only the support vectors, which will give us the lambda I non-zero. For all other samples, right here, non-support vectors, they will give us the fx value that is greater than 1 or smaller than -1. So that is this case. So we are going to choose lambda I to be 0 for non-support vectors. Yeah? Okay. Now, we can just simply summarize the result like this. When we talk about the minimization problem using the Lagrange multiplier, and then we are going to min max L, and then which give us the W in this form, as well as it satisfy this constraint with the Lagrange multiplier greater than or equal to 0, that is non-negative value, as well as we need to satisfy this condition. Yeah, this condition just to make sure that all the samples, they are correctly classified. Yeah, by properly choosing lambda I, which will give us this condition. And then now I'm going to talk a little bit more about once we have fx, and then what I mean that is once we have W transpose x plus W, we have two cases. We have two versions. The first one, that is the hard classifier. The hard classifier, that means we are going to apply the psi function into this hyperplane so that it gives us this result. If this Wx plus W0, that is the z. If z that is less than 0, which will return us -1. Greater than z greater than 0, that is +1. That means no matter what, when we input a sample into this x, and then this hyperplane hard classifier will give us either +1 or -1, either class 1 or class 2. Okay, another one we call this is the soft classifier. So we have a soft function right here. So that means when this Wx plus W0, that is less than -1, which will give us -1. If it is in between -1 and +1, which just return the value of z. That is this value right here. If z that is greater than 1, it just return +1. That means when the z value that is larger than the absolute value of 1, it will just round it off or crop it to +1 or -1 to indicate that it belongs to +1 or -1 classes. In the middle, and then it is just a linear function. Okay. Now, to consolidate the idea right here, when we have this example, we have a line right here. This is the WTX plus W0. Yeah, so this one which maximize the margin. So the shifted version, it would be something like that. And then because this is the +1, this is the -1, so that means when you substitute this point into, when you substitute x5 into this function, so Wx5 plus W0, which will give you -1. And then when you substitute this, this is x2. What I'm talking about, that is this point. This is x5. So when you substitute x5 plus W0, which will give you +1, that is this label. Yeah. Okay. So now these two guys, they are the support vectors. So according to this equation, it will just give you, because we will just find out that this lambda 1 that is 0, this lambda 3 that is 0, because they are non-support vectors. Only lambda 5 and lambda 2, that is these two guys, they are non-zero. So W will be, according to this equation, it will be W2 2, lambda 2, y2, x2 plus this guy, that is lambda 5. Lambda 5, y5, x5, that is w. All the rest, all the rest sample points, the lambda, they are 0.